Welcome back as we wrap up chapter 9. So today we're going to continue a conversation about geometric series, but today we're going to cover something unique. We're going to talk about what happens if our series is infinite. All right, so this is the first time that we're talking about what if the series has no end. Because sometimes for some geometric series, you can actually still find the sum of something infinite. Now this seems absolutely mind-boggling, right? Well, let's see how this plays out. So I want you to picture a sequence with a rate of 3. So you're getting terms 1, 3, 9, 27, 81, so on and so forth. Okay, now what I've plotted for you is this is the sum of that first term, the sum of the first two terms, the sum of the first three terms, the sum of the first four terms. Now, what you're noticing is when that rate is 3, your sum just keeps jumping. Every single time getting bigger and bigger and bigger. It's growing without bound, right? Your sum is just going to keep getting bigger and bigger. When that happens, we call this a divergent series, okay? It means we're not going to be able to determine that sum. Okay, it's getting too big, too fast, it's not settling in on a number. So that is divergent and it will not have an infinite sum. Now, things get more interesting when r is a fraction between 0 and 1 or between 0 and -1. Those work the same, okay? And what you end up seeing is this. Now, when I track the sum after the first term, the sum after the second term, the sum after the third term, so on and so forth. When your rate is between 0 and 1 or between 0 and -1, what ends up happening is it approaches a limit. The sum actually has a bound to it. The sum will only be able to get so big. You may be wondering why that is. Well, look at this. Each term is getting smaller. Each term of the sequence is getting closer and closer to 0. So every time you're adding a number that's smaller. And because you're adding a number that's smaller, you're adding a number that's close and closer to 0, it creates a limit of how big your sum can get. And it actually creates a bound here, in this case at 1. The sum is going to be approaching 1 as it goes off to infinity. Okay, so that's this idea of convergent and divergent. When this happens, this is called a convergent series and it will have a sum. And again, it converges because the rate is between -1 and 1. Okay, so you're talking about a decimal or a fraction. And so as each term is getting smaller, it means that the sum is actually going to hone in on a particular number as you go out to infinity. All right, so let's see how this works in practice. All right, so we have a new formula for this situation, okay? And the reason for that is because if you plug infinity in for n, well, some weird things start happening, okay? So they gave us a new formula to work with. On the bright side, it's actually an easier formula than the one we were using yesterday. So that's kind of to our benefit. So here we have to take into account when we're talking about going off to infinity, we have to take a few things into account. Is it a geometric series? And what is R? Okay, so let's take a look at this right here. So what am I doing to go from term to term? Well, it looks like I'm multiplying by a half. Okay, 1 times 1/2 gives me 1/2, times half again gives me 1/4. Having a rate of 0.5 checks out. This will converge. Okay? So this one is going to converge. The rate is in that right window of opportunity. It's between a -1 and 1. Therefore, I can use my new formula. My new summation formula is the first term divided by 1 minus that rate. All right? So again, this is going to be so much easier to plug into the calculator. So 1 divided by 1 minus that rate. Oops. 1 divided by 1 minus that rate. And it gives me a 2. All right, so this is going to add up to 2. All right, remember summation notation. So this one right here, remember your rate comes from whatever is being taken to the exponent, whatever has the power. Well, in this case, that equates to -1.25. That does not work. Okay, it's not inside that -1 to +1 window. So this one is going to diverge, and you don't even have to find the sum because there isn't a sum as it goes off to infinity. All right. So let's look at this one. Now, this one is a little bit tricky, okay? Because you may not know offhand what you're multiplying by to go from term to term. Okay, now it looks like to me I'm multiplying the top by 3 and the bottom by 2. Okay, but again, if you need to, you can always take the second term divided by the first term. So if you need to do that, 3/4 divided by 1/2, that gives me 1.5, which is the same as I found right here. But if the rate is 1.5, again, that's too big. Okay, it means it's going to diverge and it won't work. All right, what about this one? So here, notice my alternating pattern. So I know my r is going to be negative. And notice every time the bottom is multiplying by 3. So what that really means is I'm multiplying by -1/3. Okay, or again, you could always do your trick of second term divided by the first term, so -1/9 divided by 1/3. But if you check it, you're going to get the same thing that I just put up on the board. So this one does converge. So we can actually use our formula on this one. So our sum is going to be our first term divided by 1 minus the rate. All right, so let's plug that into the calculator. So our first term is 1/3 divided by 1 minus that rate. And what does that give me? Gives me 0.25. So this series, as it trails off to infinity, is going to be getting infinitely close to summing up to 0.25. And finally, our last one. So here, our rate of 2/3, that does check out. This is going to converge, okay? Remember, we're looking for rates between a -1 and a +1. So our sum is going to be the first term. Well, if I plug 1 into there, I'm just going to get 2/3. 1 minus that rate of 2/3. Let's plug that into our calculator. So 2/3 divided by 1 minus 2/3. And that gives me a sum of 2. All right, so now that we've talked about that, I do want to take a moment to just review everything we've done with geometric sequences, okay? Because this is the end of the chapter, and we need to make sure that we're ready for that chapter test. So let's go back and review everything that we've done. Recursive and explicit formulas. So remember, recursively, we're going to be seeing that we're multiplying by 5 each time. So recursively, we have to start with that first term. Remember, that's the key to recursive things. Label out your first term, then every future term is based on what do I do to my previous term. In this case, I'm going to multiply by 5. Explicitly, you take that first term and you just multiply by the rate to the n minus 1 power. And it tells me if I want to find a 7, well, I just plug in 7. 7 minus 1 is 6. So 6 times 5 to the 6th power, 109,375. So again, you just have to re-familiarize yourself with all these formulas that we know. Geometric mean. Remember, for geometric mean, plus or minus, when you multiply those together and then square root it. So 70 times 17.5 gives me 1,225. Square root that, and that gives me plus or minus 35. So remember how to do geometric means. You need the plus or minus, and you need to know your square rooting when you multiply those two numbers together. And then, what about this? When I know two terms that are not sequential. Well, remember, you use the explicit geometric rule to find that missing information. I know A1, I know we're talking about the fourth term, and I know what that fourth term is. What I need to know is R. So let's use the geometric structure to find R. 192 equals the first term times a rate which we don't know to the n minus 1 power. Let's divide that 3 off. So 64 equals r to the third. So I cube root both sides now. I need to get rid of that third power. So I cube root both sides to get my rate is 4. Once I know that my rate is 4, well, now I have everything I need to actually write my geometric rule. So now that is my official geometric rule. And if I want the fourth term, I want the eighth term, 8 minus 1 is 7. 49,152. All right, so a lot of good stuff in here and a lot of good review. So take a moment, please, write that summary for me, and then make sure you're ready to come back to class tomorrow and do your practice work.